Assalamualaikum warahmatullahi ta'ala wabarakatuh. Welcome to another video on MCTE 2311 Signal and System Analysis. In this video, I will talk about Introduction to Modeling. In the study of signal and system analysis, model is referring to a mathematical equation that represent the behavior or characteristic of a physical system. Okay, for example, electrical system or mechanical system. This mathematical model, okay, can be obtained through two methods. So the first one is the true derivation from physical law such as Newton's law or Kirchhoff's law, and the second method is through experiment by observing the input-output relationship of the system. Okay, this method is also known as system identification. In the time domain, okay, analysis, the mathematical model of the system is called differential equation. In this slide, I will explain in detail the two methods that is used to obtain the system model. Okay, for example, let's say here you have a system, okay, represented by S of t, where the input to the system is x of t and the output from the system is y of t. Now, using the first method, which is derivation from physical law, this method is used if we know the physical law that can be used, okay, to relate the system. Okay, for example, you know that you can use Newton's law, okay, which is summation of force. Okay, so we can derive the system model. Okay, for example, let's say you want to model a linear actuator. Okay, shown in this figure, which is a linear electromechanical actuator. So if I'm to represent this system in terms of a block diagram, it will look like this, okay, where you have here a DC motor. So let's say if we connect the terminal of the DC motor to a voltage, maybe plus minus 2 volt, okay, the voltage will induce current, armature current, and then this current will rotate the shaft of the DC motor. Okay, so in this case, electrical signal is converted to a mechanical rotation of the motor shaft. And then this rotational motion is then converted to translational motion, okay, denoted by X over here, of the ball screw mechanism. So at the end, we have a linear actuator, a linear motion. So the equation, okay, related to this linear actuator in terms of the armature current, the rotation, and the translational motion, okay, is readily available in the textbook. Okay, it is derived using the Kirchhoff's voltage law and also Newton's law. For the second method, which is the system identification, okay, we use this method usually if the system is very complex and it is difficult to derive the system model using physical law. Okay, so in this case, usually we know the input and the output of the system, which is obtained from either experiment or simulation. And then again, we want to determine S of t, okay, which is the system model. For example, let's say you're asked to model a railway bogie. Okay, so here I have the model of the system. Okay, I built using a software called Simpac. Okay, so this is a complete railway with the car body and two bogie at the front and at the back. And at the bogie here, we have the primary suspension system and the secondary suspension system. So the input to this system is known as the stochastic input, which is basically the irregularity of the railway track over here, okay, that is in contact with the wheel. So that act as the input to the system. Now, if we put sensor at the car body or at the axle box down here on the bogie level, we can measure the X, Y, and Z acceleration of the car body or the axle box. Okay, and this acceleration, okay, I show here example of the acceleration in y direction. There are two signals here, which is the actual acceleration obtained from the actual train and the Simpac acceleration, which is obtained from simulation. So from these signals, we can derive or we can get the mathematical model of the bogie. which is a complex system and difficult to derive using a physical law, okay, or first law. So I will stop here for this video. I will show you how to model a electrical system, how to model an electrical system in the next video. Thank you.